Hello, in this video we will be discussing the energy stored in a capacitor. In one of our previous videos we mentioned that the main job or the main purpose of having a capacitor is to store charges in a capacitor or on the plates of the capacitor, or also we mentioned is to store energy in a capacitor. So in this video we will be discussing the energy stored in a capacitor and also how we can calculate this energy stored. So to store charge in a capacitor, the battery must do the work, and this means it is storing energy to be used later. So when I have a capacitor, it's empty, I fill it with charges and make it fully charged. That is for the idea that I will be using this capacitor later on to act like a battery. Now the energy stored is equal to the work done by the battery to move the charges from one plate to the other. So if I assume I have two parallel plates and they are connected with, let's see, a battery here. So the left plate connected with the positive terminal of the battery and the negative terminal of the battery connected with the right plate. Now we're saying it is the work, it will be the work done by the battery to move the charges. So as a start, I will have a one charge being moved from one side to the other side. So we're taking this charge, take it all the way around to make this side of the plate negative, and that's gonna take some time. Now instantly we know that the work equal the force times the distance between the two plates, and the force will be the electric force acting because of the electric field. So in other words, I can say that electrostatic force, it is the Q times E, and that's multiply the distance between the two plates. Now we know also from another occasion that the potential difference between the two plates, actually it is the electric field multiplied by the distance of the two plates. So from here I can say that the work done by the battery to move these charges equal the charge multiplied with the potential difference between the two plates. So if I want to calculate the work done by the battery to move the first charge, instantly the first charge, that will equal 0, because the fact is there is no potential difference to move the charge between the two plates. So the work will be done here is 0. But if I want to take or take it as, I will think about it as the whole amount of charges after a while. So the work will be done equal, it's, let's say it's the big Q for the whole amount of charges multiplied by the potential difference between the plates. From here we can think about it as it is the average work done in the middle, and that's what gave us the formula of the work. It is half of the charge multiplied by the potential difference between the two plates. Okay? So from this formula I can calculate how much work done to move the charges between the two plates of the capacitor. Okay? Now we can't really ignore the fact that is the work also representing the potential energy or the energy stored in a capacitor. So from here, I can rewrite my formula here as it is the energy stored or the potential energy stored in a capacitor to be half Q multiplied by the potential difference between the two plates. Okay? That's the idea or the concept of having energy stored in a capacitor, and we know that this energy is stored in the electric field between the two plates. Now, this formula of the energy stored in a capacitor could be presented in different forms, and we can visit that simply by saying, all right, the potential energy is stored in a capacitor. It is half the amount of charge multiplied with the potential difference. But we know for sure that the capacitance equal the amount of charges divided on the potential difference. That's in our previous video when we defined the farad unit. We said a farad unit, its means or can be represented as a 1 coulomb over 1 volt. Now I can rearrange this formula to be V equal charge over the capacitance, or I can rearrange it as Q equal those capacitance multiplied by the voltage. They are all similar, but it's just different form. I'll use these different forms as an advantage to replace them here. So let's say I want to replace this voltage here by this formula here and see what's going to happen with our potential energy. It will be half Q, and it's going to be Q over C to give us that it is half Q square over the capacitance. That will be the second form to calculate the energy stored in a capacitor. Or I can use the Q here and replace it with the Q from this one. Let's change maybe the color to help us identify that we have different ones. It will be the potential energy equal half CV, that's in replacing the Q, multiplied with the voltage, all right? And from here, we will have it as a half the capacitance multiplied by square root of the potential difference. And that will be the third form of the potential energy stored in a capacitor. So I have the original one here where we created the whole formula. That is one, that's the second one, that's the third one. All of them, they serve the same purpose. They can be used for the same idea of calculating or finding or determining the energy stored in a capacitor. But which one should I pick? It depends on what is given in the question. Okay? So I'll try to solve a quick example, simple one, to practice the idea of having or calculating the work done by a capacitor, by a battery to charge a capacitor. So how much work does a 3-volt battery do when it stores 4.8 to the power minus 13 coulomb of charge on the plates of a capacitor? So I have my capacitor's plate, doesn't matter the shape, it's not mentioned here, so I can assume it is like this. Now I know how much the charge is, the Q, it is 4.8 to the power minus 13 coulomb, and I know the battery supplying the two plates with the charge equal 3 volt. All right, so we have 3 different formulas we said for the potential or energy or for the work start, we can mention them quickly here. We said the potential energy here, it is half QV, or I can say it is half Q square over C, or I can say it is half CV square. So I can pick any one of these to solve the problem, generally speaking, but when I look to my example, I only have the charge and also the potential difference. So these are the only thing I've been given in my example. So because of that, I will choose the first one to help me solving my question. So we'll say it is half 4.8 10 to the power minus 13. 3. We just do the math. That will give us the value. If we do some calculation, it will be 7.2 10 to the power minus 13 joule. And that will be how much work has been done by this battery to store this amount of charges in this capacitor. Okay, thank you, and hopefully we'll see you in another video.